Today I'm going to be speaking about meta-analysis for complex data structures. One kind of data structure is when some or all of the studies in the meta-analysis provide data for more than one independent subgroup. For example, the study might report an effect size for males and separately for females. Another kind is data for multiple outcomes. For example, a study might report data for scores on a math test and also for scores on a reading test. Another possibility is data for multiple time points. A study might report an outcome at 1 month, again at 6 months, and again at a year. And finally, we have data for multiple comparison groups. A common example of this is where studies have a single placebo group and then 3 or 4 treatment groups where each of the treatment groups is being compared against the same placebo group. It's going to turn out that the biggest difference here is between this first one, independent subgroups, and the other 3. And that difference is going to be that when we are dealing with independent subgroups, the data for each subgroup is independent of the data for the other subgroups. The subgroup called males has one set of subjects, and the subgroup called females has a separate set of subjects. So for most purposes, these 2 subgroups can be considered independent of each other. By contrast, in the last 3 of these, multiple outcomes, multiple time points, and multiple comparison groups, typically we have a situation where the same data comes, where all of the data comes from the same people, so that we have the same students, for example, giving us an estimate of the effect of the intervention on math, and also on the effect of the intervention on reading. Or we have the same subjects giving us information about the impact of the intervention at 1 month and again at 3 months. And similarly, when we have multiple comparison groups, we have the same set of placebo patients, for example, having an impact on all estimates of the effect size. The effect size for treatment 1, treatment 2, and treatment 3 all use the same placebo group. So in the first case, the data tend to be independent. In the last 3 cases, we're going to assume that there's some amount of interdependence among the effect sizes. I'm going to be discussing this, how we deal with complex data structures, for 2 kinds of analyses. The first is going to be where we're trying to combine effects across the different outcomes or subgroups. So, for example, we might want to get an estimate of the overall effect regardless of whether the subjects were male or female. We simply want to collapse across that. Or we might want to get an estimate of the overall academic improvement without regard for whether we're dealing with math or reading. We want a sort of a common estimate. The second situation is where we're interested in comparing the effects. We specifically want to compare the effect for males versus the effect for females, or we want to compare the impact of the intervention on math as compared with the impact of the intervention on reading. So in the first case, we're collapsing across these different entities. In the second case, we are isolating each one, and we're comparing the 2 of them. Before turning to complex data structures, let's start with a simple meta-analysis. There's one point that I want to make before moving on. Let's assume that we have a study. We're going to say insert column 4 study names, insert column 4 effect size data. The data is continuous, unmatched groups, post data only. We want to enter the mean, standard deviation, and sample size in each group. We're going to call the group simply group A and group B. The first study is study 1. It has a mean of 10.5. The second study is the second group is group B. It has a mean of 10. Each group has a standard deviation of 10 points. Each group has a sample size of 100. The effect direction is automatic. What we can see over here is that the raw difference in means is 0.5 and the variance is 2. Just to simplify this a little bit, I'm going to get rid of the standardized difference in means on hedges G. I'm going to click Customize Computed Effect Size Display. I'm going to change the default display to the raw difference in means. I'm going to get rid of the standardized difference in hedges G. So what I have over here now is the difference in means, the standard error, and the variance. The variance is an estimate of how much error there is, and so 1 over the variance is going to provide an estimate. First of all, it's going to give us the weight that's going to be assigned to the study. But it's helpful to think of the weight as the amount of information that that study is providing. The larger the weight, the more information that study gives us. In all of today's discussion, I'm going to be working with the fixed effect model, which simply means that the only error that we need to be concerned about is the within study error. We're going to ignore the situation where the true effect size varies from one study to the next. Everything that we're speaking about today can be applied also to the random effects model, but I think this discussion is going to be complicated enough if we deal only with one source of error. So I'd like to focus on that, and then later we can think about how to apply this to the random effects model. Just to show you what would happen if we tried to run an analysis with just the one study, we can see over here that the difference in means is 0.5. The standard error, as we said a minute ago, is 1.4. The variance is 2.0. And if we want to see the weights that are being assigned to this study, we can show the raw weight. The raw weight is 0.5. 1 divided by 2 is 0.5. That's the weight. It is our estimate of how much information this study is providing. The larger the weight, the more the information. Let's come back over here to data entry. Let me simply copy this study 10 times. I'm going to copy it down to here, and I'm going to give each study a different name. We'll call that study 2, study 3, study 4, study 5, study 6, study 7, study 8, study 9, and study 10. Okay. Now we're going to run the analysis. Again, I'm going to display the raw weight for each of these. For each of these, the variance was 2, giving us a weight of 0.5. So for any one of them alone, the amount of error, if you will, is going to be 1 over the weight. 1 over 0.5 would give us 2. But when we sum all of these, when we synthesize all of these to get an overall estimate of the combined effect, the sum of these, the sum of the weights, the sum of the information is no longer 0.5, it's 0.5 times 10, which is 5.0. The information is 0.5, the variance error is 2, 1 divided by 0.5 is 2, but for the combined effect, the total amount of information is 5, the error is 0.2. Let me come back over here and do one more thing. This is going to become important in a couple of minutes. Rather than keeping the estimate for group A at 10.5, I'm going to change some of them to 10.7. So we'll copy that to study 4, and to study 6, and to study 8, and to study 10. So now half of these have an effect size of 0.5, half of them have an effect size of 0.7. I'm going to save this and call it basic data. And if I go ahead and run the analysis now, the overall effect is now going to be 0.6 rather than 0.5, because half of them are 0.5, half of them are 0.7. Overall, we have 0.6. But the variance for each of them is still 2, and the variance for the composite is still 0.2. Okay, now let's go ahead and take a look at how this same thing looks in Excel. I should also mention, by the way, that if you want to click on calculations, you can actually see how the calculations are done. For each of them, we have the point estimate, we have the variance. Over here, we have a column which gives us the weights. It's 0.5 in each case. We have a column which gives us the weight times the point estimate, so that's going to be 0.25. In some cases, 0.35 in others. What we then do is we add up this column to get 3, we add up this column to get 5, and we take 3 divided by 5, which gives us 0.6, which is the overall estimate of the effect. And then we take 1 over 5 to get 0.2, which is the overall estimate of the variance. And those values, of course, are the values that we saw over here, 0.6 for the effect and 0.2 for the variance. Let's look at the same thing in Excel. I have exactly the same 10 studies over here. I have the same effect sizes, 0.5, 0.7, 0.5, 0.7, and so on. The variance in each case is 2. What I've done over here is I've skipped the step where we entered the standard deviation and sample size to compute the variance. We simply are coming over here, picking up the variance and entering that, just to keep this as simple as possible. We have the weight for each study. The weight, you can see the formula over here. 1 over the variance gives us the weight. This column over here is simply the effect size times the weight, which gives us ES times the weight. As we saw a minute ago, we're getting values over here of 0.25 and 0.35, 0.25 and 0.35. Down at the bottom, we sum the weights to get 0.5. We sum this column to get 3. That's the same thing that we saw over here. When we click on both models, when we click on calculations, this column gives us a sum of 5. This column gives us a sum of 3. We come back over here. If we take 3 divided by 5, we get the mean. If we take 1 over 5, we get the variance. If we take the square root of the variance, we get the standard error. If we take the mean divided by the standard error, we get the z-score. So 0.6 divided by 0.447 gives us a z-score of 1.342. And then we can get the p-value corresponding to that z-score. The formula is up here. And the p-value would be 0.180. In general, I'm not a big fan of p-values. I tend to focus on the effect size with the lower and upper limits. In this case, I'm focusing on the z-value and the p-value because I want to keep this very focused. My goal over here is simply to show you how the variance changes and to make the point that certain ways of doing the analysis are equivalent, even if they might not appear that way on the surface, that they'll give you the same estimate of the variance and therefore the same estimate of the z-value and the p-value. So the key points so far: number 1, the variance is the inverse of the information. The higher the variance, the less information we have. The lower the variance, the more information we have. When we think about doing a synthesis, the goal is to increase the amount of information that we have. That increases the precision of the estimate, decreases the variance of the estimate. And we saw a simple case over here of how that happens. As we accumulate information across 10 studies, the variance of that estimate shrinks. In this case, all of the studies had the same variance of 2. When we had 10 such studies, computed the weight for all of them, summed the weights, took 1 over the weight. The variance of the summary estimate was 0.2. Okay, so that's the basic idea I wanted to communicate so far. With that in mind, let's turn to the case where studies include more than one independent subgroup. I'm going to use the example where each study gives us an effect size both for males and for females. And the reason I use this example is that generally we would understand that each person would fall into one subgroup or the other, and therefore it's clear that the subgroups represent independent information, at least for the purposes of the present discussion. So what I've done over here is I've gone back and taken exactly the same data set that we had a minute ago, where it was listed as 10 studies. I've copied exactly the same data down here, but what previously had been study 1 and study 2, I am now calling study 1 for males and females. What previously had been studies 3 and 4, I'm now calling study 2 for males and females. So just as before we had 10 rows of information, now we have 10 rows of information. Before, every study had an effect size of 0.5 or 0.7. I have one of those in every one of these studies. And before, every row of information had a variance of 2. We have that again over here. Now, the key to this is that every line of information is independent of the other ones. One way to think about this would be that perhaps one researcher had gone out and done a study where he included a group of men and also included a group of women, and decided to publish them both as part of the same paper. So there we have one paper that reports data for males and another one for females. Another researcher perhaps had gone out and done a study using males and one using females, and decided to publish that as two separate papers. So we have one paper for males and a separate paper for females. This somewhat arbitrary decision to publish this as one paper or two really does not affect the amount of information that we have. So when it comes time to do the analysis, we actually could put it into the program as 10 separate rows, with each row representing independent information, where each row has a variance of 2, and that would work. And alternatively, the program allows us to put it in as 5 studies, where each study has 2 subgroups within it. And I'm going to show you in a minute using CMA that you can do that. But logically, either approach should give us exactly the same answer, because either approach is using exactly the same amount of information. Again, if we think of the weight as the amount of information that's being brought to bear on the problem, the weight is the same in both cases. The sum of the weights is the same in both cases. And it turns out that that's exactly what happens. Over here, we have the first approach, where we're simply going to treat the 10 rows as having no relationship to each other. So what we do is we sum the weights. Again, we have over here the same columns that we always have: a column with the effect size, a column with a variance, both of which are entered, the weight, which is simply 1 divided by the variance. In this case, 1 divided by 2 is 0.5, and a column of the effect size times the weight, which is simply this column times this one, which gives us 0.25 for the first row, 0.35 for the second. If we sum the weights, we get 5. If we sum the effect size times the weights, we get 3. And then the overall effect is 3 divided by 5, which is 0.6. And it's going to turn out that essentially all of the analyses we do are going to give us the same effect size of 0.6. What we need to focus on over here is the precision of the estimate, or the imprecision of the estimate, which is the variance. In this case, as always, the variance is 1 divided by the weights. 1 divided by 5 is 0.2. So the overall effect is 0.6 with a variance of 0.2. That's one way of doing the analysis, and it's completely appropriate. The alternative way of doing the analysis is to take each study, do a fixed effect meta-analysis on the subgroups within a study to get an overall effect for that study. So we're going to do a fixed effect meta-analysis on these 2 subgroups to get an overall effect for study 1, which we're going to put over here. You'll see over here that essentially what I've done is taken these 2 rows and collapsed them into a single row. We're going to do a fixed effect meta-analysis on these 2 rows to get an overall estimate for study 2, and so on for study 3, study 4, and study 5. And after we get these 5 estimates, we're then going to do an additional meta-analysis on these 5 studies to get an overall effect. So here we're basically doing a single meta-analysis on all 10 rows. Over here we're doing 5 meta-analyses, each one within a study, and then after we have the 5, we're going to do a meta-analysis on those 5 to get an overall effect. The way that we do a meta-analysis on these 2 subgroups to get an estimate for study 1 is exactly the same method that we've been using all along. We have to get the sum of the weights, and we have to get the sum of the column effect size times the weight. Well, the sum of the weights for these 2 studies, we have 0.5 plus 0.5, that gives us a sum of 1. And then the sum of ES times the weight, in the first case it was 0.25, and the second case is 0.35. If we sum those, we get 0.60. So the 2 values that we need over here are 1 and 0.6. before we were doing that by working vertically. Now we're doing it by working horizontally, but obviously that's an arbitrary difference. Once we have 1 and 0.6, the effect size is going to be 0.6 divided by 1, which is 0.6. The variance is going to be 1 over 1, the inverse of the sum, which is 1. And once we have the effect size and the variance, at that point we can get the standard error. It's simply the square root of this. We can get the z-value. It is simply 0.6 divided by 1. And then we can get the p-value that goes with the z-value. So at this point, we in effect have done a fixed effect meta-analysis for these two rows, and we have the results over here. Similarly, we're going to do that over here, and again we're going to get 0.6 for the effect size and 1 for the variance. We're going to get that over here, we're going to get that over here, and we're going to get that over here. So now we have done 5 meta-analyses, we have 5 separate composite scores. The last thing that we need to do is to do a meta-analysis on these 5 composite scores, and we do that the same way that we always do. For each study, or for each composite, we're going to need the weight and the effect size times the weight. Well, the weight over here is going to be 1 over the variance, so 1 over 1 gives us a weight of 1. And then we need the effect size times the weight. Well, that's going to be 0.6 times 1, which gives us 0.6. So for the first study, we have 1 and 0.6. For the second one, we have 1 and 0.6, and so on for the third, the fourth, and the fifth. And then the next thing we need to do is to sum the weights. We get 5. We need to sum the effect size times the weight. We get 3. And since these two numbers over here are identical to the numbers that we had over here, the first thing that we see is that the system is actually working, since all that we did was take this information and collapse it in one step. Here we've taken it and collapsed it in 2 steps, but logically we have to end up with the same amount of information, and so we do. And then once we have these two numbers, we can take 3 divided by 5 to get the overall mean, 1 over 5 to get the overall variance. The standard error is going to be the square root of the variance. The z is going to be 0.6 divided by 0.447, and then we get the p-value that goes with that. And as we would expect, the numbers that we're seeing over here are identical to the numbers that we're seeing over here. So again, what we see is that when we're dealing with independent subgroups within a study, we can either simply treat each row as though it were, in effect, an entirely separate study and do this, or we can we can do a synthesis on the data within each study to get an effect size for that study, and then do a meta-analysis on those effect sizes, and we get this. And in this example, and in fact in many examples, these two approaches are going to give us exactly the same answer. A little bit later I'll talk about cases where that's not exactly true, but the general idea over here is what I'm trying to convey. Let's see how we can do exactly the same thing using CMA. In CMA, I'm going to say insert column for study names, insert column for subgroups within study. That means independent subgroups within a study. Insert, in fact, let's go ahead and enter the first study. We're going to have study 1, and then again study 1, because both of these are the same study. For subgroups, we're going to have females and males. And then what I can do over here is I can click this button, and the program is automatically going to recognize that both of these are part of the same study, and when you do that, it collapses them. It's critical, obviously, that both of these studies have exactly the same name. Typically this might be something like a Cooper, 1990. And then I can say insert study. And since the program basically understands that each study has a line for males and a line for females, I can say add row for every subgroup within the study. The next study is going to be study 2. The next study is going to be study 3. The next study is going to be study 4. And the next study is going to be study 5. This little feature, by the way, comes in handy if you have some studies that have 5 or 10 or 15 different subgroups within them. It turns out that there's no requirement that every study have the same subgroups or have all of the same subgroups. So you might want to set up the first study with all of them. This is a fairly easy way to enter as many studies as you need without worrying about typographical errors. And then afterwards you can go ahead and delete the lines that you're not using. In any event, at this point we have study 1, 2, 3, 4, and 5. Within each study we have females and males. I'm going to say insert a column for effect size data, and we're going to do what we did a minute ago, which is to use continuous data, computed effect sizes, raw difference and variance, and say finish. We're going to call these groups A and B. The difference in means, let's say for the females I think was 0.7, and for the males was 0.5. The variance was 2 and 2. The effect direction is automatic. I realize that these numbers over here are precisely the reverse of what we had a minute ago, but I think in the Excel spreadsheet I had them labeled as males and females, whereas here they're labeled females and males, and so that's why I've put 0.7 over 0.5. I'm going to copy this data so that all of the studies are identical. I'm going to get rid of these two sets of columns over here. I'm going to make the difference in means my main outcome. I'm going to remove standard difference in hedges G. So this is precisely the same data that we had before. Now that we have this set up in CMA, I can show you how to do the analysis in CMA. In Excel, I showed that there were 2 options for running the analysis. One of them was simply to do an analysis on all 10 rows. The other one was to combine pairs of rows to get an effect size and variance for each study, and then do an analysis on those 5 studies. We have the same 2 options in CMA. If I click Run Analysis, the program is going to show me that first it's going to take the option where we treat each row as completely unrelated to any of the other rows. I have study 1 females, study 1 males, and so on. We have all 10 rows. Over here we can see the weight. I'm going to click on show row weight. We can see the weight that is assigned to each row, which is a weight of 0.5. And so the total amount of information is 0.5 times 10, which is 5. If I look at the calculations, by clicking over here, we have each weight is 0.5, the sum of the weights is 5, the sum of each weight times its effect size, that sum is 3. So the key numbers are 5, the amount of information, and 3. 3 divided by 5 gives us the effect size, and 1 divided by 5 gives us the variance. If we come back here, we see the effect size is 0.6 and the variance is 0.2. And again, that variance depends on the fact that the variance for each row was 2. There were 10 such rows, so the weight for each row was 0.5. 0.5 times 10 is 5. That's the total amount of information that we have over here. And again, we end up with an effect size of 0.6, a variance of 0.2. The alternative way of doing the analysis would be to compute an effect size for each study separately. If I right-click on this column over here, subgroups within studies, and I click on select by subgroup within study, down at the bottom we have the first option is use subgroup within study as the unit of analysis. Basically use each row as a separate study. That's what we did a minute ago. Alternatively, I can click use study as the unit of analysis. I click OK. What the program now does is it computes an effect size and variance for each study. You'll see now that we simply have 5 rows rather than 10. They're called study 1, study 2, study 3, and so on. For each study, rather than having a row that is labeled females and one that's labeled males, it is simply called combined. the effect size for each study, rather than having a row that says 0.5 and one that says 0.7, there is simply one value of 0.6, so that our overall effect is going to be 0.6. Critically, however, whereas before the variance for each study was the variance for each study was 2, now the variance for each study is 1. The variance is half as large because it's based on twice as much information. And by exactly the same logic, whereas the weight for each study, for each row before, had been 0.5, now the weight for each study is 1. It's twice as large because it's based on twice as much information. So before, when we summed the weights, we were summing 0.5 times 10 for a sum of 5. Now we are summing 1 times 5 for a sum of 5. So we have the same amount of information, and just as before the overall variance was 0.2, again over here the overall variance is 0.2. If we click on calculations, you will see that now again we have 5 rows rather than 10. The weights are 1 for each study. The sum of the weights is 5. The sum of the weights times the effect size is 3. 3 divided by 5 gives us 0.6, and 1 divided by 5 gives us the overall variance, which is 0.2. Critically, again, either approach is going to give you exactly the same result, and these are the same results that we saw over here, doing a direct analysis of the 10 rows, and alternatively over here, computing 5 separate effect sizes and performing an analysis on those. Okay, so that's the basic issue with subgroups within a study, when our goal is to compute an effect across all of the subgroups. Everything that we're dealing with at the moment is geared toward the goal of computing a combined effect. We're not interested in making a distinction between males and females. We simply want to know what is the impact of the treatment overall. I said a minute ago that there was a little bit of a shortcut that I was taking over here by entering the effect size and the variance for each study rather than entering the original data for each study. And I probably should explain what that is. It's a little bit tangential to what we're doing right now, but in the interest of being as accurate as I can, I wanted to just mention that, and then we'll move on. There are 2 cases where the program, when you actually enter the means and standard deviations for each group, or if we're dealing with binary data and you actually enter the cells, the 2x2 cells for each subgroup within a study, the program has a better option. It's easier to explain for the case of 2x2 cells. If we give the program the 2x2 cells for the males and the 2x2 cells for the females within a study, rather than computing the odds ratio for each subgroup and then merging the 2 odds ratios, the program actually has the option of recomputing the 2x2 table that we would have gotten if we went back to the original study and sort of manually recomputed the 2x2 table by taking the 2x2 table for males and the 2x2 table for females and adding the numbers in each cell to come out with an overall 2x2 table, and then computing the odds ratio for that. So if you're dealing with binary data, and that's the kind of information that you provide, the program will actually go back and recompute the original 2x2 table rather than doing a fixed effect analysis to combine the odds ratios. Similarly, if you're dealing with means and you provide the means and standard deviations both for the males and for the females, then rather than computing the effect size for males and the effect size for females and merging them, the program will go back and compute the mean that the author of the paper would have reported if she had actually done an analysis which did not divide the sample into males and females, but incorporated both of them. And the program, again, over here, will do that if it has the kinds of information that will enable it to do that. It does this on a study-by-study basis, so that if for some studies you actually provided the means and standard deviations, For those studies, the program will go back and recompute the original information. If for other studies you only have the effect size and the variance, then for those studies the program will use the method that I showed you in Excel. In general, the two approaches are going to give you results that are extremely similar, but the method of going back and reconstructing the original study is a little bit more accurate, and so the program does that when it is able to. Okay, now let's move on to the next situation. Okay, the key issue when we were dealing with multiple subgroups was that each subgroup was independent of the others. If we had a study that included both 200 males and 200 females, that study actually had 400 subjects in it, so we had 400 independent observations. By contrast, when we move on to multiple outcomes, I've taken the same set of data as we had before, but now for study one, rather than having males and females, we have math and reading. The assumption is that we have 200 students. 100 are assigned to treated, 100 are assigned to control. And after we use the intervention, we assess the same students both on math and reading. So while we have 400 observations, we have really only 200 subjects. Because the observations are not independent of each other, the total amount of information that we have is less than it would have been if we really had 400 students that we were working with. And because we're no longer dealing with independent observations, because the total amount of information that we have is less than it would have been if we had independent observations, we need to take that information into account in figuring out what the error is and how much weight we can assign to each study. So if we took the same approach that we took before of doing a meta-analysis and treating all of these observations as though they were independent, so that the weight for math was 0.5 and the weight for reading was 0.5, and we summed all of these weights and got a total weight of 5, representing the total of information, the total amount of information that we have, and then took 1 over 5 to get 0.2 as the error variance of the mean, that would be incorrect. This value of 5 overestimates the total amount of information that we actually have, and this variance of 0.2 underestimates the actual amount of error that we have. Therefore, what we need to do is, rather than working with these, we need to work across. What we're going to do is to compute a composite score for study 1, a composite score and the variance of that composite, where this variance is going to take into account the fact that the effect for math and the effect for reading are not independent of each other. We're going to do the same thing for study 2, study 3, and so on. After that, we're going to end up with basically a weight and we're going to end up, after we have the variance and effect size for each study, we can then combine these 5 estimates using a regular meta-analysis, and in this case the weights are going to be correct. I should point out before continuing that while this appears on the surface to be the same thing as we did over here, it is not exactly the same. There's an important difference. When we were working with independent subgroups, we used a meta-analysis to combine this information over here to get the estimate of the combined effect and the variance. By contrast, over here, what we're doing is we're not using a meta-analysis to go from here to here. Instead, what we're doing is we're using a formula. The formula to get the effect size is simply that we take the mean of these two numbers. In this example, we take 0.5 plus 0.7 and divide that whole thing by 2 to get the mean. So the mean is 0.6. More critically, for our purposes, the way that we get the variance is that we use a formula which takes into account the variance for math and the variance for reading, and also the correlation between math and reading, the number that we see over here. The formula itself is complicated enough that I'm going to put off discussing it for now. I will come back to that later in the session. But the critical thing is that this formula takes into account the correlation between the two. Initially, I've set the correlation to 0. the correlation between math and reading is not likely to be 0, but I've set the correlation to 0 to make a very important point. When the correlation is 0, the numbers that we're going to get over here for the variance are exactly the same as the numbers that we got before when we were dealing with independent subgroups, where in fact the correlation was 0. So for example, over here, the variance was 1 for each of them. Similarly over here, the variance is 1 for each of them. And when the variance is 1, the weight that we're going to be assigning is going to be 1 divided by 1, which is 1, which is the same as the weights that we assigned over here. And therefore, when we do a meta-analysis to combine these 5 studies, and we're going to do the meta-analysis the same way that we always do. The weight for this study is 1 over 1. The effect size times the weight is 1 times 0.6, which gives us 0.6. We sum that for all of the studies, we get 5. We sum that for all of this column, we get 3. The numbers that we're getting over here are exactly the same as the numbers that we got over here. The variance that we're getting over here is exactly the same as the variance that we got over here. So if it was the case that these things were independent, we would get exactly the same numbers. The point I'm trying to make is that the formula for computing the variance is consistent with everything that we've seen so far. If these items really were independent, then what we're dealing with over here would give us the same kinds of things we were getting when we were dealing with multiple subgroups. The point is that the correlation is not likely to be 0. Let's say that the correlation instead of 0 was 0.2. Let's say that I was trying to type that in over here. Let's say that the correlation instead of 0 was 0.2. What happens is the variance for each of these now increases. Rather than being a variance of 1 for each composite, the variance is now 1.2 for each composite. Since the variance has gone up, the error is greater, the amount of information has gone down. The weight for each of these, rather than being 1, is now 0.83. When we sum the weights, instead of getting 5, we get 4.16. The overall estimate of the effect hasn't changed. That's still going to be 0.6, but the variance of the effect is now 0.24 rather than 0.20, which it had been over here. The standard error, which previously had been 0.44, is now 0.49. The z-value, which previously had been 1.3, is now 1.22. And the p-value, which previously had been 0.18, is now 0.22. So the basic idea is that the estimate of the effect size hasn't changed, but the precision the estimate has become less precise. There's less information, there is more error, and everything that goes along with that. Let's say the correlation instead of 0.2 is 0.4. Now, the mean again is still the same, but the variance for each of these has gone from 1.0 to 1.2 to 1.4. The weight has gone down. The estimate of the total variance is now 0.28. What if the correlation goes to 0.6? What if the correlation goes to 0.6? The mean again stays the same, but the error for each of these goes up. The weight, the amount of information, goes down. The total weight is now 3.1, where originally it had been 5. The variance of the composite is now 0.32. Correlation goes to 0.8. Error for each of these goes up. The weight for each of them goes down. The variance is now 0.36. And finally, in the extreme situation, what if the correlation is 1? Now what happens is the variance for each composite is the same as the variance had been just for math alone. In other words, when the correlation is 1, we're saying that whatever score somebody gets on math is going to be exactly the same as the score that they get on reading. In that case, the fact that we're assessing them on reading as well as assessing them on math really provides us with no additional information. Remember that when we're taking a composite, we're saying we're not interested in the difference between math and reading. We just want some general information about how much of an impact the intervention had on their academic score in general. And if the correlation between math scores and reading scores is 1.0, it's not ever going to be that high, but this is just to make a point. If the correlation is 1, then as soon as we know somebody's math score, we also know their reading score with no error. So there's really no point in giving them the reading test. The reading test doesn't add any information to what we had. So if the amount of error that we originally had just for math was 2, if the weight that we had for math was 0.5, then adding the reading doesn't do anything. The sum of the weights is going to be 2.5, which is precisely half of what it would have been if the correlation was 0. The mean score is still 0.6, excuse me. But the variance, the error variance for this is now 0.4. It's precisely twice what it had been before. So the basic idea is that you can see as the correlation moves from 0 to 1, at one extreme, the variance for this, if the correlation is 0, the variance of the estimate is going to be exactly what it was over here when we treated these as 10 independent observations. By contrast, at the other extreme, when the variance is 1, the variance for this is going to be precisely twice what it was because we have precisely half as much information. In truth, the correlation is probably going to lie someplace in the middle, and therefore the variance for the estimate is going to lie someplace in the middle. Let's see how we handle this in CMA. In CMA, I'm going to say insert column for study names, insert column, well, let's do this. Let's say insert column for outcome names, and I'm going to call this study 1, and I'm going to copy that to the second row. For outcome, I'm going to have math and reading, and then we're going to say insert study, add a row for every outcome. We're going to call this study 2. We're going to call this study 3. We're going to call this study 4. We're going to call this study 5. By the way, you don't need to do this at the front. You can sort of generate these studies while you're entering data, and then go back and the program will collapse them for you when you ask it to. But in this case, it's just a little bit easier to do it this way. I can click this button over here, and the program will show me that it recognizes that these two lines represent the same study. The main difference from what we did before is that this time we said insert column for outcome names, whereas last time we said insert column for subgroups within the study. Subgroups are independent, outcomes are not. We're going to say insert a column for effect size data. We're going to come over here, continuous data, computed effect sizes, raw difference in means and variance for independent groups. Certainly within math, the two groups treated in control are independent. That's what we are referring to. We'll call them group A and group B. The difference in means was, let's say, 0.5 for math and 0.7 for reading. The variance was 2 and 2. The effect direction is automatic. We're going to copy this to the next set of studies. Just in case it's not clear, obviously everything that we're doing over here is also going to work when the effect size varies from one study to the next. I'm simply keeping them the same over here to isolate what happens with these different techniques and make the presentation as focused on that issue as possible. We're going to set difference in means as the primary outcome. We're going to remove the standardized difference in means, and we're going to save this and call it, let's say, table C with outcomes. And we will save that. Now remember before when we went ahead and ran an analysis, by default, for different subgroups, by default the program assumed that we were going to treat each row as independent. That's not the case now. Since we have defined these as being multiple outcomes, the program does not want you to make the mistake of treating them as independent. So by default, there's any number of things that you can do, but by default the program is simply going to pick the first outcome and present an analysis for that. What it's done over here is it's done an analysis for math, since math alphabetically comes before reading. The difference in means is 0.5. The variance for each of these is 2, and the total variance, you will notice, is 0.4. It's twice as large as the variance that we had before because it's based on only half of the information. If you right-click over here on outcomes and you say select by outcome, the program shows that there are a number of options that you can use. First of all, I should point out that you can select or deselect either one of these. If you were to deselect reading so you have only math, then in a sense you would have only one outcome left and all of the analysis would be based on math alone. In that case, everything is extremely straightforward. There's no problem of multiple outcomes, and you really don't need anything further in this lesson. I'm going to assume that you have more than one outcome and you want to combine them for each study. I should also point out, by the way, that you could have a third outcome over here, which might be gym, athletics, and you decide that you want to create a composite that involves people's scores on math and reading, but not athletics. In that case, you could deselect athletics, and all of the composites would be based on math and reading. So this is a fairly flexible system. Critically, down here, the program says for studies with multiple outcomes, what do you want to do? You can use the mean of the selected outcomes, you can use all of the selected outcomes assuming independence, or you can use the first outcome based on this sequence. Then you can move reading and math up and down. We're not going to be dealing with the third option over here. This would be useful, for example, if let's say you had multiple versions of, some kind of an achievement test. They were all supposed to measure the same thing, but one test was really good, one test was mediocre, and one test was really not that great. So if you had, for any study, you had the first test, that's the one that you want to use. If you don't have that, you'll fall back on the second. If you don't have that, you'll fall back on the third. You could choose this option over here, put a sequence in here, and basically what the program is going to do is to take the best option that's available for any given study. Again, in that case, you have only one outcome that you're using for one study, and so the question of multiple outcomes doesn't arise. So we're not going to be dealing with that over here. We're going to limit ourselves to the first two options. One of them is use all of the selected outcomes assuming independence. The program issues a warning over here, which is basically the warning that I'm going to explain to you. So when we treat these as independent, what you see is that the overall estimate is 0.6. and the variance for that estimate is 0.2. The sum of the weights is 5. If we come to the calculations, you can see that the sum of the weights is 5. Critically, this is the same thing that we got over here when we summed all of the weights and got 5. The overall estimate of the variance was 0.2. And similarly over here, if we assume the correlation of 0, the variance for the sum was 0.2. These weights over here are being shown, they're already being collapsed for 0.5 plus 0.5 gives you 1, so it's not displaying in exactly the same way as it had before. But the key thing is that the sum of the weights is 5, the same as it was over here. The variance is 0.2, the same as it is over here, and the same as it is over here. So if we tell the program to treat these as independent, generally not an appropriate idea, but if you do that, you will get exactly the same thing that we got over here, treating them as independent, or critically, that we get over here if we give the correlation as 0. But what happens if we tell the program, right-click over here, go to Select by Outcome, and say I want to use the mean of the selected outcomes? Basically what's happening now is that we are telling the program to compute a combined score for each study and treat the correlation between math and reading as 1.0. In that case, if we look at the calculations, each of these studies is being assigned a weight of 0.5 rather than a weight of 1, because we're treating the information as being cut in half. We're treating it as though we have only the information from either math or reading, but that the second one is redundant. So the sum of the weights is 2.5, and therefore if we come back here and look at these, the effect size is still 0.6, but the variance, rather than being 0.2, is now 0.4. The variance has precisely doubled. The sum of the weights is 2.5 rather than 5. And that is exactly what we're going to get over here if we tell that the correlation is 1. The variance is 0.4 rather than 0.2. The sum of the weights is 2.5 rather than 5. So that's what CMA is doing if you tell it that, that these effects are correlated. Now, obviously, it would be nice if CMA allowed you to put in a correlation other than 0 or 1. We are hard at work on a newer version of this that not only is going to allow you to put in some other estimate of the correlation, but actually will have many advanced features for dealing with correlated data. But at the moment, these are the only two options that CMA allows you. You can treat these as though they're independent, or you can treat them as though they are completely redundant with each other. If you treat them as though they are independent, then the estimate of the variance is going to be much too low. It would be 0.2. If you treat them as though they are completely redundant, the estimate of the variance is probably going to be 0.4, which is probably too high. In general, this is probably the better option. It's a more conservative option in the sense that you are overestimating the error rather than underestimating the errors. This is probably what you'd rather be doing. However, there is one other option that you can use in CMA. It requires a little bit of work, but might be the better option, and we're going to take a look at that right now. What happens if we come back over here, and let's say that we put in a correlation of 0.5, which gives us a variance of 0.3, which is really halfway between 0.2 and 0.4. And let's assume that we think that this is a reasonable variance to be using. What we now have basically for each of these studies is an effect size and the correct variance. So we can come back to CMA and come back over here. I'm going to go back to data entry, and I'm going to save this study, and let me open up a new file, and I'm going to say insert column for study names, insert column for effect size data, and I'm going to come back again to continuous data, computed effect sizes, raw mean difference and variance. And what I'm going to do over here is I'm going to say I have study 1, study 2, study 3, study 4, and study 5. The difference in means, now remember that we've taken, we're dealing with now with the composite scores, so the difference is going to be 0.6. The correct variance, let's say we come back over here, and using Excel, we discovered that the correct estimate of the variance, assuming that the correlation is 0.5, the correct estimate of the variance would be 1.5. So I'm going to come back over here and put in 1.5, and the effect direction is automatic. And I'm going to copy this 5 times. I'm going to save the file and call it summary data for outcomes. And then I'm going to run the analysis. And let me come back over here. By default, the program excuse me, was running the analysis on this. Let me change that. First of all, I can simply right-click over here and say set this to the primary index. And I don't even really need to get rid of these. I'm going to go to Run Analysis. You can also, by the way, select the index on the fly from here. But the point is now, what we're dealing with are 5 independent estimates, right? Each study provides an independent estimate. Within each study, the variance is the variance that we would have computed if we assumed the correlation between math and reading was 0.5. So that would be a correct estimate of the variance. So the variance that we're getting overall is 0.3, which precisely matches the variance that we're getting over here if we did the analysis correctly in Excel. So the point is that if you're dealing with a situation where you don't want to assume that the correlation is 0, and you also don't want to assume that the correlation is 1, you do have the option of doing this of computing the correct correlation for each study in Excel, and then simply transferring that information over to CMA and proceeding with the analysis. Notice, for example, I mean, this is reasonably straightforward. If you were going to come back here, first of all, you might want to enter an estimate of 0.5. Let's assume that you think the correlation almost certainly falls in the range of 0.5 to 0.7. You could then type in 0.7 over here, see what the variance is, come back to CMA, and let's say we go back to data entry. I'm going to customize this. Let me get rid of these two just to make it a little bit simpler. I'm going to say that these are the ones based on a correlation of 0.5. So the variable name over here is the expected, let's say, correlation. The column function is a moderator. The data type is categorical. And this is a correlation of 0.5, of correlation of 0.5. I'm going to copy that down to here. Then we can come back here and say, well, what if the correlation was 0.7? What would that give us? And it turns out now the variance is going to be 1.7. So I'm going to come back over here. I'm going to copy these, and I'm simply going to call the study 1A because we can't have the same study name twice, and this is just the simplest way to deal with it. And I'm going to say over here that the correlation is 0.7. And now I can go ahead and run the analysis. And I can say, let's say I'm going to computational options. I want to select by. I'm going to select by a moderator, which is going to be the correlation. What if I select only the cases where the correlation is 0.5? It turns out that I get an estimate of 0.6 with a variance of 0.3. And for the sake of argument, a p-value of 0.27. Then I come back and I say I want to select by, and this time I'm going to select only the cases where the correlation is 0.7, and this time the correlation, the variance is 0.3 and the p-value is 0.27. Oh, I'm sorry, I made a mistake. If I come back here, obviously I have to come back over here and put in the correct variance for these, which is 1.7. Save that, run the analysis. So the variance is 0.34 and the p-value is 0.30. So I get a sense now that if the correlation actually falls in the range of 0.5 to 0.7, that my variance is going to fall in the range of 0.3 to 0.34. The p-value is going to fall in the range of, I think it was 0.27 to 0.30. And I might conclude that as long as the correlation falls in a plausible range, that my conclusions are pretty much going to be the same, that there really is no evidence over here of a significant impact of the interaction. So the point is, well, I guess there are several points that I'm making. The first is that CMA by default will only allow you to work with a correlation that's either 0 or 1. The second point is that there are ways of bypassing this limitation aside from waiting for the next version of CMA, which is that in Excel it's fairly simple to compute the correct variance for each thing, for each study, then move that into CMA. And the last point, and perhaps one of the more important points, is that people assume that if you don't know the correlation between math and reading, there's really nothing that you can do. It turns out that in many cases, you can't come up with a plausible estimate. It might be that the correlation probably falls in the range of 0.3 to 0.7. It might be 0.4 to 0.6. It might be 0.7 to 0.9. But whatever that range is, you can sort of do an analysis using the lower end of that range and the upper end of the range. In some cases, it will turn out that as long as the correlation falls any place in that range, your conclusions are really pretty much going to be the same. In some cases, of course, it will turn out that at one end of the range, you get a different conclusion than at the other end, in which case you really don't have the satisfaction of closure. But in any event, those are the options that you currently have. I said before that I would come back and explain the formula for the variance over here. I should warn you that this formula is going to be fairly complicated and not terribly intuitive. You might want to go back and take a look at the book where we explain it in a certain amount of detail. The reason that it is not terribly easy is because it involves 3 or 4 different ideas that you probably haven't thought about in a while or ever. The first thing has to do with the relationship between the scale that we're using and the variance. Let's say, for the sake of argument, we have a test that is scaled on a range, let's say, of 1 to 10. And let's say the standard deviation for that test is 5 points. This is not 1 to 10. This is 1 to 10. God bless Excel. Now let's say that we decide that rather than using a range of 1 to 10, we want to use a range of 10 to 100. So basically what we're going to do is we're going to take the same test, but we're simply going to multiply every score by 10. What's going to happen to the standard deviation? Well, it's a basic law of statistics that if you multiply every score by 10, you have to multiply the standard deviation by the standard deviation gets multiplied by 10. So the standard deviation is going to be 50. The same, and then what happens to the variance? Well, originally the variance was 5 squared, so it was 5 squared was 25. The variance of the new scale is going to be 2500. So the basic idea is that if you multiply everything over here by 10, the variance gets multiplied by 10 squared. So the variance initially was 25. The new variance is going to be 25 times 10 squared, which is 2500. Why is this important to us? Well, it's important because when we compute the composite, we're not taking, basically what we're doing is we're rescaling this. In our example, in every case we have only 2 outcomes, and so we take the mean of them. Basically what we're doing is we're taking 0.5 and dividing it in half, and we're taking 0.7 and dividing it in half. So what we're doing, just like over here, we multiplied every score by 10, what we're doing over here is we're dividing every score by 2. So if originally the variance of this was 2, and the variance of this was 2, then on the new scale, right, so we had 0.5 as the effect size and 0.7 as the effect size, and the variance was 2, and the variance was, the variance was 2, and the variance was 2. Now we're moving to a new metric where the first score becomes 0.5 divided by 2, which is 0.25, and the second score becomes 0.7 divided by 2, which is 0.35. What's the variance of this metric going to be? Well, if over here the variance was 2 and 2, the standard deviation would have been the square root of this, which would have been 1.41, and the standard deviation over here would have been the square root of this, which would have been 1.41. So the standard deviation over here is going to be half of this one, and the standard deviation for this is going to be half of this one. Each of these is going to have a standard deviation of 0.7. What's the variance of these going to be? Well, this is going to be equal to this squared, and it's going to be equal to this squared. So basically, before doing anything, because what we've done is we have divided every effect size in half, we also have to divide the variance in half to get the new variance that's going to be relevant to what we're doing over here. Now, I sort of drew this out by starting with the variance, moving back to the standard deviation, cutting the standard deviation in half, and moving back to the variance. But you can do it in one step. In effect, what we're doing over here, you'll notice, is that if you cut the standard deviation in half, then if the standard deviation is multiplied by 0.5, then the variance is multiplied by 0.5 squared, or 0.25, right? This, in effect, is 1/4 of this. So the way that we can go to the new variance is we simply can say the new variance is going to be the old variance multiplied by 0.5 squared. Or we can say it's going to be the old variance divided by 4. Any one of those is going to give us 0.5, which is the value that we saw over here. Now, this works if we have only 2 outcomes for each study. If we had 3 outcomes for each study, it would be multiplying by 3 squared, or we would be dividing by 9, and so on. But that's the basic idea. The first thing that you need to do is to take the old variance and adjust it. The second thing we need to do when we're talking about the variance of a composite is we need to add the 2 variances. So if the variance over here is now 0.5 and the variance over here is now 0.5, we sum those to get the new variance, which is 1. And if the correlation between these 2 things is 0, then the new variance actually is simply the sum of the 2 values. It's 0.5 plus 0.5, which gives you 1. And that would be all that you need. Let me show you that over here. In fact, let me take this whole thing, copy it down over here. We want to compute the variance of these 2, and the formula is going to be D102 divided by 4 plus D103 divided by 4. Basically, that's 2 divided by 4 plus 2 divided by 4 gives us 0.5 plus 0.5, which gives us 1. So if the correlation is 0, that's all that's involved. So far we've covered 2 things. The first thing is that we need to adjust the variance because we're adjusting the scores. The second thing is that we need to sum them. Where this really begins to get, where this gets complicated is when the correlation is not 0. Let's say the correlation is 1, to take the other extreme, and the variance now jumps from 1 to 2. The reason is because the formula for the variance, I'm going to copy this over here again so that I can show you how this works. The formula for the variance, which allows for the correlation, is this. It's going to be, as we saw before, the first variance divided by 4 plus the second variance divided by 4. But there's an additional component to it, which is based on the correlation. Basically, if the correlation is 0, this whole thing over here drops out. But if the correlation is not 0, this over here adds a component to the variance, which tells us that we have to increase the error term because the errors are correlated. Over here in this formula, first of all, we have L56, which is where I've located the correlation. Then we have the square root of the first variance over 4 times the square root of the second variance over 4. So you can go back and fool with this. You should have this spreadsheet, but the basic idea is that this formula over here includes the correlation, and as the correlation goes up, this component over here is going to increase. In the extreme, this component over here is going to equal the first variance plus the second variance. So basically the total variance is going to double. To put it another way, when the correlation is 0, this whole thing over here is 0. The correlation is simply the first variance plus the second after the adjustments. When the correlation is 1, then this whole thing over here is equal to the first correlation plus the second. So the whole variance doubles. Okay, I realize that was probably a little bit complicated, and I apologize for that, but fortunately, you can actually use this spreadsheet. The only thing you need to do is to modify it to take into account how many outcomes are being used in the composite, and then rather than dividing by 4, you would be dividing by 9 if there are 3 outcomes. You'd be dividing by 16 if there are 4 outcomes, and so on. And obviously, you can have a different number of outcomes for every study. Okay, so we've covered independent subgroups and we've covered multiple outcomes. Multiple time points works exactly the same way as multiple outcomes. It's exactly the same logic. It's exactly the same procedures you would use in Excel that I showed you for outcomes, or in CMA. In CMA, you can tell the program that I want to insert a column for multiple time points, but the impact on the program will be exactly the same as it was for multiple outcomes. The program handles either one of those exactly the same way. When we come to multiple comparison groups, the situation is a little bit different. In CMA, if you tell it that you have multiple comparison groups, CMA will handle it exactly as it did for multiple outcomes or multiple time points. But if you're working with Excel, the thing is that when you're dealing with multiple outcomes or multiple time points, the best that you can do over here is to estimate the correlation. You might say, for the sake of argument, I assume the correlation is going to be around 0.5. When you're dealing with multiple comparisons, if you have a placebo that's being compared with treatment 1, treatment 2, and treatment 3, you actually can figure out what that correlation is, so you don't need to estimate it. And the way that you would do that is actually fairly simple. If, let's say that you have 4 groups, so that you have the placebo group, and you have treatment 1, and treatment 2, and treatment 3. And so you have placebo versus treatment 1, and you have placebo versus treatment 2, and you have placebo versus treatment 3. The correlation between this comparison and this comparison and this comparison is known, because assuming that you have the same number of subjects in each group, let's assume for the sake of argument you have 100 here, and 100 here, and 100 here, and 100 here. If we want to look at this comparison and want to know how correlated it is with this one, obviously the idea over here is we want to know what's the impact of treatment overall as compared to placebo. We don't care to distinguish between treatment 1 and treatment 2. Well, the correlation between this and this is 1.0, because it's exactly the same subjects on the same score. The correlation between this and this is 0, because it's a completely different set of patients. So if for half the patients the correlation is 1, and for the other half the correlation is 0, then overall the correlation between these two outcomes is 0.5. The situation changes a little bit if you have different numbers of subjects in the different groups, but that's basically the idea, is that you can actually compute what the correlation is. So you don't need to to estimate it. And so you can enter the data over here, then return it to CMA using the method that I showed you. But in this case, the correlation is known, and so you don't need to think about upper and lower bounds. Something else that you can do if you're dealing with multiple treatment groups, if you are dealing with binary data based on 2x2 tables, you can actually go back and recreate what those tables would look like. So, for example, if you know that for placebo you had 20 people that responded and 80 people that didn't, and then in treatment 1 you had a certain number that responded and a certain number that didn't, and in treatment 2 the same thing. You can take the placebo cells and enter them once, and take the treatment cells and collapse them, so that basically what you end up with is a 2x2 table that has the correct number of patients for placebo and the correct number of patients for the composite of the treated groups. In that case, you don't need to think about multiple comparisons or anything else. You just enter this as a single line for each study, and you get the correct results. One thing you might want to think about is that you might want to initially go back and enter it separately using the techniques that I was showing you to make sure that it makes sense to collapse treatment 1 and treatment 2. Obviously, if it turns out that treatment 1 and treatment 2 are very different in their effectiveness, then you might not want to go back and collapse them. So to this point, I've sort of laid out the issues, and I've tried to show how you can work with these different kinds of complex data structures when your goal is to combine effects. When you're interested in ignoring the differences between males and females and getting an overall effect for all people, or if you're interested in ignoring the differences between math and reading and getting an overall assessment of the impact on academic achievement, or if you want to ignore the difference between outcome at 1 month and 6 months, or if you simply are interested in the effect of treatment in general against placebo and you want to ignore the difference between treatment 1 and treatment 2. The next thing we need to do is to move on to the question of what happens when you want to compare effects. So you specifically want to compare the impact for males versus females, or you want to look at the difference in the effect size for math versus reading, or you want to look at the difference in the effect size, let's say for 1 month versus 6 months, or you want to look at the difference in effect for treatment 1 versus treatment 2. And we're going to turn to that now. It turns out that a lot of what we've been doing already is applicable to this, and therefore I think this part of the discussion is going to go a little bit more quickly. When we're interested in looking at differences, let me start with the case of subgroups within studies. This is the same file that we had before. Again, I can set this up so that we have study 1, 2, 3, and 4. Within each study we have females and males. We run the analysis, and what we looked at before was an attempt to get an overall estimate of the summary effect, ignoring differences between males and females. We do have this option. If what we want to do is focus on the difference between males and females, we can go to computational options, compare groups, group by, and we're going to group by subgroup within study, in which case the program will do one analysis for the females, a separate analysis for the males. The estimate for the females was 0.7, the estimate for the males is 0.5. This over here is the overall estimate as we saw before. But critically, we can go to the next table, and what we have over here is 0.7 for the females, 0.5 for the males. The variance is 0.4 for this and 0.4 for this. And if we wanted to compare 0.7 versus 0.5 using this variance and this one, the p-value for that is 0.823. I am not going to go into detail right now just because it is the hour is late, but if we come back to the Excel spreadsheet we were looking at a minute ago, you will see that on the bottom we have sheet 1 and sheet 2. Sheet 2 is looking at these differences, and what you see we have over here is the computation of the effect for studies well, I guess this would be for the studies that were based on males. The overall effect is 0.5, the variance is 0.4. Here we have a meta-analysis for the females. The overall effect is 0.7, the variance is 0.4. If we wanted to go ahead now and compare those two, the difference would be 0.7 minus 0.5, which is 0.2. The variance, you simply sum the two of them. 0.4 plus 0.4 gives us 0.8. The standard error is going to be the square root of that. The z-value is going to be 0.2 divided by 0.89, which gives us 0.22, and the p-value is 0.82. And so that's exactly the same as the numbers that we were seeing over here. The p-value is 0.82. The next situation we might want to look at somewhat quickly, if we come back over here, and now let's deal with the case of multiple outcomes. So we have over here math and reading. This is the same analysis we were looking at a few minutes ago. And if we come back over here and go to the, for studies with multiple outcomes, we want to use the mean of all selected outcomes, assuming independence. We click OK. As I said before, this analysis is not valid, but we can do group by, and we're going to group by outcome, and the program gives us an estimate for the math, which is 0.5, an estimate for the reading, which is 0.7, and then we go to the next table, and what we're looking at over here is 0.5 versus 0.7 with a p-value of 0.823. Now, you might have recognized that the p-value that we're getting over here is precisely the same as the p-value that we got when we were comparing independent subgroups. And the reason for that is that what the program is doing over here when dealing with multiple outcomes is that it's treating them as independent of each other. In fact, if you remember when we come back here, we had selected to treat these as independent of each other. And when you do treat it, as I explained earlier, when you treat these as independent, then what we're going to get for multiple outcomes is exactly the same as what we're going to be getting for multiple subgroups. Now here's where things get a little bit interesting. You will remember that when we were dealing with sheet 1, when we're dealing with the composites, a correlation of 0 gave us a variance of an overall variance of 0.2, whereas a correlation of 1 gave us an overall variance of 0.4. So as the correlation got lower and lower, or rather as the correlation approached 0, the variance was, the error was minimized. As the correlation approached 1, the error was maximized. It turns out that when we go to differences, the situation is exactly the reverse. So if we come down over here, and over here we have sort of the same structure that we had before. Now we're looking at differences, and we can enter a correlation of 0 or anything else that we want. When the correlation is 0, the variance is at its highest, and in this case the p-value was 0.823, which is what we saw before. If we move the correlation is 0, the variance is, the overall variance is 0.8. When that's the variance of the difference. If the correlation is moved up to 0.5, the variance gets smaller, and if the correlation approaches 0.99, the variance over here approaches 0. So it's precisely the opposite of what it was when we were dealing with a summary score. What this means for us is that whereas it was the case when we were dealing with composites that the conservative position, the position that gave us the largest estimate of the variance, was to assume that the correlation was 1, when we are dealing with differences, the conservative estimate, the estimate that's going to give us the largest amount of error, is a correlation of 0. And so that is what CMA is using over here. And that's how we ended up with a p-value of 0.83. However, the situation over here is exactly the same as it was before. We do have the option of putting in what might be our best estimate of the correlation, let's say an estimate of 0.5. And if we do that, we now get these correct, or at least more plausible estimates of the variance. What we can do is go back into CMA. We can enter for each study, we can enter basically 5 lines. In each case, the effect size is basically going to be the difference between male and female. Study, insert column for study names, insert a column for effect size data. So we have over here study 1. The difference in means is now really the difference in the difference in means. It's 0.2. The variance we saw over here is 2, based on a correlation of 0.5. The effect direction is automatic. We can copy this. So we have study 2, study 3, study 4, and study 5. Let me just show you one thing before I move on to this. If we came back over here and treated the correlation as 0, the variance that we'd be getting in each case is 4. Let me go back and plug that in. And then we go ahead and run the analysis. And we're going to look at the analysis for the raw difference in means. What we're going to be getting over here is an estimate of the overall variance of 8, and the p-value is 0.823. Remember last time when we were looking at this, when we actually had a set of lines corresponding to math and another set corresponding to reading, the estimates that we were getting over here were 0.5 and 0.7. Therefore, we needed to look at the difference between them, and to do that we had to go to the next table. In this case, by contrast, the estimates that we're getting are actually an estimate of the difference between math and reading. And therefore, it is this over here, this 0.2 is actually the difference, and that's what we care about. The p-value for that is 0.823, which matches what we were seeing over here, 0.823 when the correlation is 0. If I change the correlation to 0.5, and we come back over here, and I go back to data entry, and the variance in this case is supposed to be 2 in each case, so I'm going to make those variances 2, and then it turns out that the overall variance is 0.4 and the overall p-value is 0.75. So again, the limitation in CMA is that if you're looking at the difference between two outcomes, the only option is to assume that the correlation is 0. This gives you a way of assuming that the correlation is 0.2 or 0.5 or any other value that you think is plausible. So it's a way of bypassing the limitation in CMA. Okay, that's it for now. I apologize that some of this was a little bit rough. I am planning to revise it in the near future. You might want to come back and have another look at it the next chance you have. Our website is www.metaanalysis.com. and thank you very much for your attention.